Greetings and welcome to the complete lecture for Chapter 1 of Chemistry 221, and I'm really glad to have you here. This chapter is kind of the introduction to the whole world of chemistry that I hope to share with you throughout this class as well as next term's Chem 222 and Chem 223, and I'm really glad to have you here. It shows you're interested, and I have a lot of really cool things to share with you. Now, Chemistry 221, and officially as it's known at Mount Hood Community College as Chemistry 221Z, along with the accompanying Chemistry 227Z lab. But anyway, I'm just going to call it Chemistry 221. Chemistry 221 is a great introduction to the course, and this course is meant for majors, so people that are interested in, for example, medicine, in physics, biology, engineering, stuff like that, they would want to take the Chemistry 221 classes. And so that's what this whole series of videos will be focused around. And I'll show you through these complete lectures the different topics in each chapter that we go through this class, and it should be a pretty fun time. The website for this class is mhchem.org/221, and everyone is welcome to view this website. It's not just for my students or anything like that. And I have a lot more learning materials on there that you might find interesting. For the class, I always recommend that students purchase the Chemistry 221 Companion, which is a collection of the labs we're going to do, as well as the problem sets, some study guides. You'll have printed versions of the notes I'm going to use here that you can mark along with you as you want to, as well as sample quizzes, all that kind of jazz on there. So if you are taking the class, I do encourage you to get it, but of course it's absolutely up to you. So without further ado, let's check out chemistry and Chemistry 221 and see what kind of things this class can offer. When you think of the term chemistry, what exactly do you think of? And chemistry is actually a very old science. Now, it hasn't always been known as chemistry per se, but it is something that people have been very interested in. And in ancient Egypt, they used, I'm probably going to mispronounce this, chemia, I believe, and it was basically, that's where they were studying embalming the dead, which was used for pharaohs and all that kind of stuff. And later on, they extended this area of thought into metallurgy, so using metals and stuff to create their things, which is kind of cool. Now, chemistry, because it started, in my opinion anyway, as something that was used for dead people, for embalming the dead, kind of was always seen as a cult. And I think that has kind of followed chemistry into the modern day, because sometimes chemistry is seen as weird and strange and stuff like that. But honestly, it's a really cool field, okay? So just hang tight with me and we will check this out. But chemistry is something that's been around for a long time, and we're continuing to learn about it even today. Chemistry itself is the scientific study of the properties and behavior of matter and energy. All right, so when it comes down to what a current definition of chemistry is, I would say that chemists are just really interested in how matter behaves, what you can do with it, how you get it there in the first place. And in addition to matter, energy is actually a big part of it too. Chemistry is a physical science, all right, and a physical science, which also includes things like physics, some engineering, stuff like that, very heavy into measurement units, energy, stuff like that. So we will sometimes reach over into physics a little bit for some of our information, but most of the time, of course, it'll be just on chemistry.
Chemistry is the science of matter, of its properties, and of its transformations. All matter is made from about 100 elemental forms, the elements. Intrinsic to matter is energy. The waves of the ocean are energy made manifest and obvious. But energy permeates even the most subtle interactions of matter and is fundamental to chemistry.
Notice in the video there how they said that all matter is made up of about 100 elements, which is about right. There's 118 elements right now, and you can think of elements as like the building blocks of all other compounds, everything that you know and see around you. So if you had some coffee, perhaps, that's chemistry. If you use a cell phone, that's definitely chemistry. So those 100 plus elements, those 100 plus building blocks are really important to everything that we have to study in chemistry. Now, chemistry, as I said, has been studied by thousands of years. It started in Egypt, arguably, with the Khamia, and then it has transformed over time into many different things. So there's an Arabic version, Al-Khamia, then Alchemy is where, of course, maybe you've heard of. That's where people were trying to transform things into gold, more or less. In 1661, Boyle, who was considered a chemist, created a book called Chemistry, where he used a Y in there, but I won't hold that against him. And then, of course, chemistry is important too. Now, for a long time, chemistry was dominated by the idea that there's only 4 elements: earth, water, air, and fire. And that silly little periodic table in the left-hand corner there is kind of part of it. That's Aristotle and his group from ancient Greek. And that's too bad, because that theory really dominated science for a long time, and it was only relatively recent, well, 500 years, I guess that's not really recent, but you get the idea, that anyway, people started to break away from that. And of course, that's good, because there's a lot more to do than just earth, air, fire, and water. Chemistry is sometimes referred to as the central science because it connects with so many different fields. And in that picture right there, you can see how chemistry is part of chemical physics within physics itself. It's also connected to chemical engineering, which is big. Definitely biochemistry and biology and medicine, of course, are connected. All the environmental things. Food science, so important, of course. Geology, geochemistry, and even mathematics, computer science have connections to chemistry as well. So chemistry is a lot of times seen as a doorway that you pass through. And once you pass through it, all these other areas are open. So you may take chemistry and not do a lot of chemistry in your future. And that's totally fine, by the way. I want you to find your own path, all that jazz. But anyway, just realize that you definitely have a lot more options upon taking and hopefully understanding chemistry. Now, the major types of chemistry that chemists use are, there's basically 4 or 5 of them, but the biggest ones, in my opinion, are organic chemistry and inorganic chemistry. Now, organic chemistry you may have heard of before. It's usually a full year, second year chemistry class. So after the Chem 221 through Chem 223 series, you might take the organic chemistry series. But organic chemistry basically just focuses on carbon, nitrogen, oxygen, hydrogen, and a couple other elements. So not a lot of them, but there's a lot of use of those elements. That's where all of the pharmaceuticals come from, medicines come from, our bodies mostly use those and stuff. So it's a pretty important field. Now, I personally am an inorganic chemist. I was focused more on metals, but really inorganic chemistry is about everything that's not carbon. And there's a lot of elements. I said there's more than 100 of them. So if you cut out the 4 or 5 that are part of organic, there's a lot of chemistry in there. A lot of things left to be explored. Now, inorganic chemists may not have the uses always that organic chemistry has. Like organic chemistry, you're trying to solve, cancer drugs and stuff like that. However, there are a lot of uses, and I'll tell you, as we'll see in a later lecture, colors in inorganic chemistry are much cooler than organic, and we'll talk about that more later. But if you like color, inorganic chemistry is for you. Now, in addition to those kind, analytical chemistry, very important. Analytical chemistry is a type of chemistry that talks about how much and what kind of stuff you have in a sample. It uses often what's called spectroscopy, which we'll talk about later. That's basically light as an analysis tool. If you're a fan of CSI kind of shows, they're always using analytical chemistry techniques to figure out what's in the blood, what the poison was, and stuff like that. Now, physical chemistry is also very important, though. Physical chemistry is where chemistry, physics, and even calculus converge. So it's a pretty heavy kind of a field. But in this, then you get ways to figure out how gases behave. You can model them using math and stuff like that. It's a powerful field. There aren't very many physical chemists, but the ones that are there are really important. And a lot of the things we're going to talk about in this class come from the studies of physical scientists. Now, the newest kid on the block is biochemistry or biochemical chemistry, and that's where biology and chemistry converge, and this is becoming a huge field. Definitely, this is really, really important. It's basically the chemistry of life and how things function, and everybody needs to understand more about how the body works. Biochemists, and in cooperation with medical people and biologists, are really good about analyzing these things, so it's a really cool field. We use chemistry chemistry every day. You're using it right now because you're breathing, hopefully anyway. Wake up. No, I'm just joking. Okay, prof hat back on. I'll say that once in a while when I'm saying something really stupid, so apologies. All right, back to your regular scheduled programming. So we use chemistry every day. Breathing, definitely that's chemistry. Eating food, digesting it and stuff, that's chemistry. Plastic is really used a lot around us, for better or worse. We'll talk about that more later too. But plastic is everywhere. Like right now I have kind of a remote control here that I'm using while I'm recording this. That's got plastic in it, and you can probably see plastic things around you, so that's important. But number one probably in your world, and mine anyway, is a cell phone. And cell phones, wow, they have so many different elements inside them. It's just crazy. The batteries, that's chemistry. The pieces inside that make the electrons flow so that you see things on the screen, that's chemistry. The components of the case, I mean, it's just everything about it. So obviously chemistry is important. Let's talk more about it and see if we can figure out then how this all puts together, how it all comes together to make something like a cell phone, which is pretty cool. Now, when you're talking about chemistry, you have to realize that atoms are really, really small. All right. And I'm not just talking really small. I'm talking really, really small. So if you go to the sink right now and you let about a teaspoon of water go down the sink, intentionally or unintentionally, that teaspoon of water has more molecules of water in it than there are teaspoons of water in the Atlantic Ocean. Now, let's just think about that for a second. Atlantic Ocean is big. If you haven't seen it, it's like the Pacific Ocean. You can't see Europe or Africa or anything like that. It's a big, big ocean. And if you were to go out there with a teaspoon and, go 1 scoop, 2 scoop, et cetera, there's a lot of teaspoons. I mean, a lot of teaspoons. However, your teaspoon of water that you put down the drain has more molecules in it than there are teaspoons in the Atlantic Ocean. So, wow, atoms are small. If there's that many molecules in a teaspoon, then that must mean they are not just small, they're freaking small. So in chemistry, we have to use different ways of thinking about the world because what we see may not be what's happening on the small level. So I'm going to talk sometimes in this class about macroscopic, and that's just the world of what we see and do. That's the cell phone world. That's the world of when you go get something to drink from the refrigerator, the things that you and I see in our day-to-day world. But we're also going to talk about what's usually called atomic, but sometimes called microscopic world, and that's the world of atoms, all right? Because sometimes we have to visualize what's happening on this atomic scale to understand some of the things that are happening in the macroscopic scale. The reason I try and stay away from microscopic is actually bigger than atomic, and microscopic is more the world of biology. But anyway, it is the same thing. It's a very, very small world, and we'll have to shrink ourselves down in the terms of chemistry to the level of the atom to make sense of things. And finally, sometimes it's useful to talk about the symbolic world, and that's just using symbols and nomenclature to understand and talk about what's happening with colleagues, all right? Because it's hard to visualize something and share that visualization with another person. But if you use symbols and you use ideas that are common to converse with your colleagues, then you can start making sense. Sharing ideas is what makes the world go around.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light.
So this is kind of a great overview of the three different domains and what they represent. Now, first of all, in the upper right-hand corner, when you saw that little balloon exploding, what was happening is inside the balloon, you have hydrogen. And when hydrogen has a little bit of a flare, basically a spark, if you will, it can ignite with the oxygen to make water. And it's a lot of energy is released, and you can hear the boom kind of thing right there. So that's the macroscopic world. All right, that's what's happening when you and I watch this this reaction happening. But you might think, wonder what exactly is happening on that level, Dr. Russell? Well, great question, random student. In the left-hand corner, you see the atomic representation. So on the atomic level, inside the yellow balloon there, you have the white atoms, and those white atoms are hydrogen. And we'll talk about more about why this is the case later. But hydrogen comes in pairs. Right now, that's all you need to worry about. And hydrogen then, when you have the spark, the hydrogen then ignites, and outside the yellow balloon are those red molecules, pairs of molecules once again. That's oxygen. And again, we'll talk about what's all happening here in a little bit. But anyway, the hydrogen, when ignited, reacts with the oxygen outside. A lot of energy is created, and you end up making water. So in the lower screen there, you've got the red oxygen atom between the two white hydrogens. That's water, H2O. And that's what's created. And in the process, a lot of energy is given off. So atomic level, that's what's happening. The little pairs of hydrogens are reacting with the pairs of oxygens to make the pairs of water. Notice that kind of V structure for water. We'll talk about that later this quarter. That's for a future lecture. But anyway, now if I'm going to refer to this when I'm talking to you outside of this video, I don't want to try and describe pairs of oxygens and hydrogens, blah, blah, blah. So in the lower right-hand corner is a chemical reaction, which is a symbolic way of representing how this works. And as it turns out, you're going to need two of those H2 molecules to react with one O2 molecule to make two H2O molecules. And the G there stands for gas, so that tells you what the final phase of this stuff is. You can see there's an arrow, so to the left is kind of like what you start with. We'll call it the reactants. To the right is what you end up with, the products. That's the symbolic representation. So in chemistry, all of these perspectives are important, and we'll use them interchangeably sometimes to describe the things that are happening. This is an example showing some different phases of water. You can see actually well, you can't really see them, but anyway, you can, on the macroscopic world, all right, you see the ocean, you see the big iceberg kind of floating there and stuff in the water. And even though you can't see it, all of the air we breathe has water in it, water vapor. So you're seeing all three versions of water. You're seeing it as a solid, which is ice in the middle. You're seeing it as the liquid water in the bottom. And even though you can't see it, the air does have water gas. And then at the atomic level there, you can see in those circles, you can see that gases are actually kind of spread out while the solids are kind of close to each other in wild forms. And in liquids, they're close to each other, but it's a little bit more random. So again, this is just another representation of the ways that we'll use this quarter to talk about chemical reactions and what's happening. One thing we have to think about in chemistry is the phase of matter. If you want some water, you're probably going to go get a glass of water. You probably wouldn't go get a piece of ice to try and suck on, although that would work, although it's just a little bit more awkward. And I definitely don't think you would take water vapor, i.e. gaseous water, and try and use that. You'd want the liquid water. So knowing what phase you have is really important. Now, in the planet Earth, there are three main phases that are important, and they're called solid, liquid, and gas. And a solid, like the ice cube, has very rigid space with fixed volume. So it's very structured. You can throw it at each other, blah, 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 and stuff like that's cool. Now, liquid water, which is probably what you want to drink then, flows. It doesn't have a fixed shape. It does have a connection, one molecule to the other, but it's a lot different. It takes on the shape of the container. If you put a piece of ice in a glass, it stays the piece of ice, but liquid will kind of merge and figure out what kind of container you have. So there's definitely differences between those. And gases just expand to fill the shape and volume of the container. They don't have fixed shapes or volumes. They're very, very flexible. So gases, liquids, and solids, we'll talk about all of those in this class. However, in the universe, the most common phase of matter is referred to as plasma. And plasma, which is kind of rare on the Earth, is very, very common outside of the Earth. So for example, the sun is basically a big source of plasma. We do see plasma on the Earth in the form of lightning and stuff like that. But anyway, plasma is basically gaseous matter that's electrically charged, and it's a whole nother ballgame. We'll talk about that more next term in Chemistry 222, but for right now at least, just kind of keep that in the back of your mind. So again, here's water as a vapor, as a solid, and a liquid. You can see the differences. And again, if you want something to drink, you're probably going to want the liquid version and not ice or, for example, gaseous water. But it's not just water. There's bromine in the upper right-hand corner. Bromine can be a solid. It can be turned into a liquid pretty readily. It's kind of a nasty, dark brown, red kind of thing. And the gas is also relevant, and you can see it. It's kind of a reddish haze and stuff above the bromine. It's a lot more dangerous to deal with than water, but it is something that chemists deal with, and if you're safe, you can deal with it too.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
So in chemistry, we use something called the kinetic molecular theory to talk about how the different phases are different from each other. And KMT, which we'll abbreviate KMT a lot for kinetic molecular theory, is the theory that's used. And you can see from the pictures, their solids are very, very tight together, all right? They have not a lot of room between the molecules, and they all move together as one. Liquids, there is a connection between them, but it's more loose, if you will. It's more flexible. So that's why liquids will fill the container you pour them into, but the liquids don't kind of go off on their own either. Gases, on the other hand, have no control over each other. They're very independent molecules. They'll take up and fill whatever volume you set them to. And of course, they will also float away if you're not paying attention stuff, which is something to remember. One consideration that chemists and also material scientists and stuff like that need to think about is the energy required to turn solids into liquids or liquids into gas. And vice versa, sometimes it's nice to think about the energy required to turn gases into liquids and liquids into solids. And this is something we will talk about this quarter definitely. But two terms I'm going to use here to describe these processes are endothermic and exothermic. Now, an endothermic reaction takes energy. You need energy to make that happen. And anytime you go solid to liquid or liquid to gas, it's an endothermic reaction. So having a solid go to a liquid won't happen unless you add energy to it. Same for liquid to gas. On the other hand, the opposite processes are exothermic. They release energy and stuff when they happen. So when you have, for example, a gas going to a liquid, energy is actually released. And going from a liquid to a solid, energy is released as well. Now, usually endothermic reactions, if you have an endothermic reaction happen, it takes energy, so your container will feel cold because usually it absorbs energy from the outside to make the inside reaction happen. So the container itself ends up feeling kind of cold. Likewise, an exothermic reaction, usually the reaction then, the container feels hot because energy is released in the process. So all of your fireworks, making water, as I talked about earlier, all those kind of things, those are exothermic. Energy is released. You can maybe see it. You can feel it if you feel the container, stuff like that. On the other hand, if you've ever used a cold pack, like after a sports injury, those feel cold, which is intentional. Those take energy to happen, so those are considered endothermic. And we will talk more about this later, but this is one of the considerations that chemists must use in order to make that happen. Now, in the middle lower picture right there are different terms that are used to represent this. So a solid going to a liquid, there's an arrow pointing up, that's melting process. So if you melt something, that's a solid going to a liquid. On the other hand, a liquid freezing, going back into a solid, oops, I gave it away there. A liquid going back into a solid, that's freezing, all right? And so these are just terms that we'll introduce later on. So liquids going to gas, you vaporize them, or it's vaporization. On the other hand, if you want your gas to go back to a liquid, that's condensation. And finally, you can have a solid go directly to a gas and a gas go directly to a solid. Now, a solid going to a gas is something you may have seen if you've ever used dry ice, which is carbon dioxide. Carbon dioxide goes straight from a solid to a gas. It sublimes, or it's the sublimation process. It is possible to take the CO2 and condense it back into a solid, solid. That's called deposition. And we'll talk about these terms more later, but the most important thing here is if I talk about endothermic or exothermic, endothermic, it takes energy and the container would feel cold. On the other hand, exothermic releases energy and the container will feel hot. To understand science, we have to talk about different kinds of measurements that we're going to take. And the most important one probably is mass. And mass is very important in chemistry. Now, mass and weight get mixed up a lot. And in chemistry, we usually don't make a big deal of it. But I want to talk about the official rules of how this all works. Mass is literally a measure of the matter in an object. So if you make a measurement in grams, kilograms, micrograms, nanograms, etc., that's the mass. It talks about how much mass is inside the object, which is great. Weight, which is what a lot of times people confuse with mass, is officially a force that gravity exerts on an object. And weight and mass can be different, all right? When you measure, if you've ever measured yourself in pounds, like on a scale, that's technically the weight. And that has to do with gravity. And the reason why scientists don't usually like using weight is that weight can be different if you're on a different planet or on the moon or something like that. So your weight is different on the Earth than it is in Mars. So you can see up there in the picture in the upper right-hand corner, there's a person with a mass of 50 kilograms, and on the Earth, that would be a weight of about 110 pounds. But on Mars, the weight would be only 42 pounds. However, notice that the mass is the same. So chemists usually use mass in grams and kilograms, stuff like that. We don't usually use weight. And of course, in space, where you don't have any gravity, usually it would be totally messed up. But again, the mass would be the same. So that's why chemists use mass whenever possible. There's something called the law of conservation of matter, which I'll sometimes abbreviate the law of mass action, that just says that mass can't be created or destroyed. And it's very helpful when you balance a chemical reaction, when you want to know what one chemical turns into later. And we'll talk about this more later. So just realize that officially you should use mass for measurements when it comes to things. Don't use weight, all right? If you call it weight, and even I might call it weight by once in a while, which is fine, just realize that technically we should all be using mass for measurements and not weight. By the way, weight is often done also in newtons, which is a type of unit, as well as pounds. But again, we're going to try and steer clear of those and just use grams, kilograms, nanograms, stuff like that. Now, another thing that scientists have to think about is if you have a pure substance or a mixture, all right? And mixtures kind of come in two different varieties. A heterogeneous mixture is when you can see different kinds of matter in the same thing. So, for example, if you have a sample of river water and there's some rocks in it, well, that's a heterogeneous mixture, all right? You can see then the different things inside it. A chocolate chip cookie would be another example. You see the cookie and you see the chocolate chips. Those you can see a difference in them, all right? Heterogeneous things are usually pretty mellow to separate, not always, but more often than not. And you can identify them by color, different types of matter, et cetera, et cetera. Now, homogeneous mixtures, though, are more difficult to understand if they're pure or not, because they look just like one substance. So, for example, coffee, my beloved coffee, anyway, it's a long story. Anyway, coffee is definitely a homogeneous mixture. It has caffeine, it has water, it's got some flavor of some sort in there. Hard to know. On the other hand, sugar water looks exactly like water. It's when you dissolve it up, all right? And if you were to drink it, you would certainly know the difference because sugar water is sweet and regular water is just water, all right? So that's why it's important to know if you have a mixture or a substance. Pure substances are probably most helpful to chemists because you can start with them and make them into other things, which is cool. If you have a mixture, then you have to be careful because maybe the other component, the thing you're not as much interested, will react in some way to make it more difficult. That being said, a solution is a type of homogeneous mixture which can be very helpful to chemists because the reactivity is faster and stuff like that. So there's a lot more to this than it is. Of all the pure substances, the ones that are important to chemists are usually compounds or elements. If you take some of my 100 plus elements from the periodic table and mix them together, that's when you can make compounds. And you can take compounds compounds and in theory break them up back into the elements. But you can't break an element into a compound. That wouldn't make any sense. You can break a compound down to an element, and we'll talk about this more later. Elements, though, are literally like our building blocks of everything. All right, they're really important. I like to think about the elements as being like letters of the alphabet. And in the English language, there's 26 letters. Well, in my chemical language, I have 118 letters, if you will. And imagine all the words that can be made from the 26 letters of the English language. You can make tons of combinations of things when it comes to my values, my 118 letters. I can make them into compounds, which are kind of like words, and there's just a whole bunch of them, which is crazy. So when it comes to elements, which are literally the building blocks of everything, the smallest piece of an element is called the atom. And you can't break atoms down and still have the element. They can be broken into other things. We'll talk about that later, but the smallest piece of the element is the atom. And again, the periodic table is so important because it lists all of these building blocks. You can see them, you can figure out their names, and there's different uses for them. Compounds are just mixtures of elements, but here's the thing. They have definite proportions by mass, and that's important. So for example, water, which is a compound, it's a combination of hydrogen and oxygen. Water is always 2 parts hydrogen to 1 part oxygen, or H2O, as chemists would call it. It will never be H2O2, which would be 2 parts hydrogen to 2 parts oxygen, or HO, or H3O, or any combination like that. So compounds have definite combinations of elements, and they don't vary from there, which is cool. Now, in theory, you can break compounds back down into the elements, so that's always a possibility, at least in theory. In the lower right-hand corner are some examples. Nitrogen dioxide, NO2, is a combination of nitrogen and oxygen. Carbon dioxide, which you might have heard of before, carbon and oxygen. So you could break carbon dioxide down into carbon and oxygen, at least in theory. We'll talk more about that later. The elements are very different from each other. Some of them are solids, some of them are liquids, some of them are gases. Some of them, like sodium, you can cut with a knife. On the other hand, some of them, like aluminum, would be much more difficult. And of course, bromine right there is a liquid with a gas phase over it. So they all have very different properties, but you can't break them down into simpler substances. They have to they can be combined into more complex compounds, but they can't be broken down. Like you can't break aluminum down into sodium, stuff like that. Compounds, again, are just mixtures of elements with definite ratios by mass. So one of my favorite compounds of all time is caffeine. Yes, I live on caffeine. My blood is caffeine. Anyway, no, sorry, Prophet, back on. Caffeine has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And caffeine always has that ratio. So you wouldn't have all of that without an oxygen, only have 1 oxygen and have caffeine. It might be something different, but it's not going to be caffeine. And that's really important. That structure there is pretty cool. We'll start talking about why the molecules make structures like that in a future lecture. The first person to define element and use that term was a person named Lavoisier. And Lavoisier was an important chemist around the late 1700s. He was one of the ones to use the idea of elements as the building blocks, and we'll talk more about Lavoisier as well in a future lecture. In this class and in these lectures, I'm going to have what I call iClicker questions. And iClicker questions are just a chance for you to assess how you're doing with the knowledge so far. And if this was an actual class, you could participate and get extra credit for it. Now, you can't do that in this example because this is just a video. But if you attend the actual lectures, this is a way you can get some extra credit. You purchase an iClicker subscription on your smartphone, and you can participate in the lectures while I give them to give extra credit. And I encourage you to talk about that with me if you have any questions. But for right now, what we're going to do is I'm just going to give you some sample questions and you can think about it. So it says, which of the following is not a compound? If you look at those choices right there, one of them is not a compound. Remember, a compound is when you have a mixture of elements in definitive ratios. So salt, sodium chloride, is NaCl. That would be a compound. And water, H2O, 2 parts hydrogen to 1 part part oxygen. That's a compound. But potassium, K right there, potassium's actually on the periodic table. It's number 19 if you have a periodic table in front of you. So potassium is an element. That is not a compound. That's one of the building blocks of things. You can make potassium nitrate and potassium chloride, etc., etc. But potassium itself is not a compound. It's an element. Table sugar and drinking alcohol, those are both examples of things around you that you might use and stuff like that. Anyway, those are compounds. They have definitive ratios. So table sugar has 12 carbons, 22 hydrogens, and 11 oxygens. Drinking alcohol has a total of 2 carbons, 6 hydrogens, and 1 oxygen. And we'll talk about later why the structure there for drinking alcohol looks different than the structure for table sugar. There's a reason for that. We'll talk about that later. But the important part here, they're both compounds. They're different from each other. They have different ratios of elements in the compound, so that's why they're different. Atoms are fascinating. Atoms are the smallest piece of the element that still has the properties of that element. All right. So for example, in the left-hand corner, that little animation, that shows some carbon atoms. Each one of those little tiny spheres is actually a carbon atom. And they can take, if you will, now like home movies that shows how these things are interacting. All matter moves around a little bit at normal temperatures. So this shows then the movement of carbon atoms at whatever temperature they took this at. If you were at absolute zero, which we'll talk about later, then in theory that matter would stop. But most of the time we're not at absolute zero, so that's why the movement happens. Now the right-hand picture there shows some copper atoms. Copper is another one of the elements on the periodic table. There's the distance on it. A distance across is 1.8 nanometers. That's for the copper atom. It's very, very small. All right. So these are pretty small little atoms. Now in that little picture, the little bumps there, little mountains, those are each copper atoms, and they're on a surface of silica, which is a silicon thing. But anyway, that shows the copper atoms kind of saying there. Now, what's fascinating about all of this is that it wasn't long ago that chemists had no pictures of atoms because they're very, very small. It's smaller than most light that we use. We'll talk about this later. So it was very, very difficult to get pictures. But now with current technology, they're able to get little pictures and little movies, which is just fantastic as a chemist to be able to see these things and how they interact, what they connect to. Pretty cool. Now on the periodic table, which is listed in the upper right-hand corner right there, those again are the elements, all right? And the elements are really cool. Now each of the little symbols on the periodic table stands for a longer name. So for example, number 1, that H there stands for hydrogen, and number 2, the HE stands for helium. So the symbols, there's always 1, sometimes 2 letters. The first letter is always capitalized, and the second letter is always lowercase. So if you're a person that likes to write in all uppercase letters, start writing lowercase. Chemists will get really freaked out by that, and I will be the same, I'll be honest. So you must write it big H, little e for helium. You can't write big H, big E for helium. That's a big faux pas. But anyway, this guy named Berzelius was the first one to think about that, which is kind of cool. Right now, there are 118 elements, but since I've been teaching at Mount Hood, that number has changed. Initially, there was more like 104 elements, and then over time, they started to add more and more and more, and now they get to 118, which is pretty cool. I am very excited for the next several elements because if they can get to element 121, it's going to actually change the shape of the periodic table. So you can see right now number 118, OG, is around. When they get to number 121, which is pretty close, there's going to be some big changes in the chemistry world. But they haven't gotten it yet, so we'll talk about that later if it happens, and also talk about why I'm excited to get to 121. There's a few pre-biblical elements. So before about 2,000 years ago, they all had different symbols. At least some of them did, but there weren't very many known. So in the last 2,000 years, there's been a lot of changes when it comes to chemistry. Big surprise, but it's kind of cool to think about the ones what they used to use and the ones that we're using now. Originally, Mendeleev was the person that kind of thought about organizing the elements as a periodic table. Initially, what he did is he tried to organize them by the mass, how much the atom weighs, and if you will. And we'll talk more about that as we go through and stuff here a little bit. But that didn't work out too well. All right, Mendeleev's idea of putting them by mass didn't really work out very well. So what they did instead is they moved it then to what's called the atomic number. And we'll talk about what the atomic number means later, but the atomic number worked out really well. Now notice that this periodic table lists only elements up to 112, and the last element picture I showed you had a periodic table up to 118. Periodic tables are almost inevitably out of date, so just get ready for it. But anyway, it was really cool, and Mendeleev's idea to kind of organize them turned out to be super cool. Mendeleev was able to predict the existence of a couple elements there, gallium, germanium, scandium, and technetium, elements that at his time hadn't been found yet, and they were found later. So he was able to predict it, which is pretty cool. Now on the periodic table, there's a couple terms we need to talk about right away. In the upper right-hand corner, the blue elements, those are called nonmetals. And hydrogen, which is also a nonmetal, plus those ones on the upper right, are pretty important to chemists, and we'll talk about that. On the left-hand side, all the ones in kind of the off yellowish kind of color, those are metals. So most of the periodic table is made of metals on there. And then the green elements that are listed right there, those are called metalloids. And metalloids have a combination of metal properties and non-metal properties. We'll talk more about that as we go through the course. But just realize non-metals in the upper right, plus hydrogen, metals, basically all the rest of the elements are metals, going to be pretty important for some of the discussions we talk about. This is a periodic table. Anyway, kind of fun stuff like that. But again, you've got that same problem. The elements are always being updated, so you're not going to have the same kind of thesis. There's a big piece now which should be complete because, again, the elements go to 118. So anyway, just let you know, maybe having a periodic table isn't the best idea unless you are really into chemistry like me, who drools over this picture every time I see it, but that's another story. So in addition to the metals on the left-hand side, the nonmetals on the upper right-hand side, and those metalloids kind of going down the middle there, it's also good to know what a group and a period is. Now, groups and periods are pretty cool. Periods on the periodic table go left to right. So in the upper video animation there, you can see the combination of the red lines. Those are the elements in the different periods. So the first period literally has just hydrogen and helium, not too much. And the second period would be lithium, Li through neon on the right, and E. And periods have their use for them, but they're not as important as the groups. And in the lower right-hand corner there, you can see the groups in the periodic table. They go up to down, if you will, top to bottom. Groups are pretty important. A lot of chemical reactivity is defined by what group the element it is in. And we're going to see that the reactivity of pieces in the same group are often similar to each other. So for example, in group 1A, you can see there's hydrogen, lithium, Na is sodium, K is potassium. We're going to see that lithium, sodium, and potassium all have a lot of chemical similarities to them. Hydrogen does too, but hydrogen's kind of a different thing because it's a nonmetal. So we'll talk more about this as we go through the course. A couple of group names, though, I would like you to know. Group 1A, those are called the alkali metals, and they're very important for lots of different processes. Sodium in sodium chloride is an alkali metal, as well as potassium, stuff like that. Now, right next door is group 2A. That's the alkaline earth metals, and those are also important. Magnesium, calcium, beryllium, stuff like that. Notice the similarities in the names, alkali and alkaline earth. And look, I'm just the messenger. I didn't make these names, okay? They sound very similar, but alkali is group 1A, and alkaline earth is group 2A. Halogens are on the far right-hand side, group 7A. Halogens are also very, very important. Fluorine, chlorine, bromine, iodine. We'll talk about those quite a bit as we go through the class. And then on the very far right, group 8A, those are called the noble gases. Helium, neon, argon, krypton, etc., etc. By the way, notice how the groups have a 1A, 2A, this kind of designation to them. There are different versions of the periodic table, but in this class, what I'm going to use is I'm going to use 1As and 2As on the far left, and on the far right then, you can see there's 3A, 4A, 5A, all all the way over to 8A. And in the middle, there are the B groups. All right. And there are different versions of the periodic table, but this is the version that we're going to use in this class. And I'll try to make translations if you're using one, but try to get a periodic table with that kind of designation on them. It's usually Roman numerals. So instead of a number 1A, it's Roman numeral 1A, etc. But just realize that's what we'll talk about. Now, the B groups in the middle, those are called transition metals. They're also very important. And in the lower parts there, those two rows, which are kind of by themselves, those are called the lanthanides and the actinides. They're also metals. They're kind of like transition metals, but they have their own kind of special things. We'll talk about all of this as we go through the class. You've got some elements. What can you do with them? How do you know you have what you have? This kind of stuff. Great question. So we're going to talk now about physical and chemical properties. All right. And properties are just one way that we can tell one substance from another, all right? And sometimes it's obvious because of what it looks like, but sometimes you need special techniques to figure out which particular element you have. So a physical property, all right, is just a characteristic of matter, and if you use it, it doesn't change the composition of the substance, which is really important. So if you do a density measurement on a substance, you're not changing the atoms and how they move around. You have this, and you can do it 10 times if you want to. It'll keep using it. The color of a substance is another physical property, which is actually really helpful. In geology, they use the hardness scale sometimes for doing things, which is great. Melting, boiling point, stuff like that. Now, a physical change is a change that can happen without, again, changing the chemical composition. So if you melt a substance, you turn a solid into a liquid. In theory, you can take that liquid and remake it a solid. All right, you can freeze it again. You haven't changed the substance at all. It's still the same substance. That's different from a chemical property. Now, chemical properties are very, very useful, but usually you have to sacrifice a small amount of sample to figure out what's actually happening. So you've probably heard about flame tests that are sometimes used. Maybe you've heard about toxicity tests, or if you want to know the amount of acidity or amount of base that's in a substance. Those are all chemical tests, and they're great. They help the chemist figure out what it is, but you have to sacrifice a little bit of sample to make that happen. So chemical changes usually accompany chemical properties. You're actually changing the composition of the material inside there. So in the upper right-hand corner there, you got poor Coyote. He just used some TNT, apparently trying to get little Roadrunner there on the left-hand side of that picture. That would be definitely a chemical change. You can see that it's a lot different. You wouldn't want to do that in real life, of course. TNT would be very dangerous. But anyway, in this silly comic strip anyway, that would be a great example of a chemical change. If you've ever looked at big trucks sometimes traveling on the freeway, or if you've seen big containers of chemicals, they'll have this kind of hazard diamond, which talks about the chemical properties of what's inside. And if there's a problem, like with a container especially, then the people, the first responders need to know, like, are there health hazards, or can it detonate, stuff like that. And these are the different symbols you can see inside there, which is just wild. They're very important and stuff, and you can look up more about them, but these are all essentially types of hazards and stuff related to chemical properties of the substances being transported or stored. So here's a question you might see. It says, which of the following is not a physical change? Now remember, the physical changes don't affect the composition of the chemicals inside there. So we want to look for something which will affect how the substances themselves are used. So freezing, the first one, a liquid to form a solid, that's not changing the chemical parts at all. You're just changing the states of matter from a liquid to a solid, and that would be a physical change. So that's not the answer. If you dissolve a solid to form a solution, all right, that's usually not a problem either. You can usually get the solid back if you evaporate the water, for example. So usually that would be a physical change as well. You can get the original materials back if you're careful. Evaporation, turning liquid into a gas, that would be a physical change, because in theory you could collect the gas, turn it back into a liquid. However, if you take a piece of paper and you burn it, it would be very difficult, I would argue impossible even, to get that ash stuff left back into the original paper form. So that would be a great example of a chemical change. It's hard to get that piece of paper back once you've burned it, all right? Probably impossible, let's be honest. But anyway, so that would be a chemical change, not a physical change. The last one there, you're turning a solid, ice, into a vapor, gas. That's a sublimation. Sublimation, solids to liquids, solids to gases, stuff like that. All of those things are physical properties. Chemical properties, it would be hard to go backwards if you had to. Once in a while, we'll talk about extensive and intensive properties. Extensive properties just depend on the amount of matter that's present. So, for example, it makes a big difference if you have 30 grams versus 0.3 grams, or if you have 20 milliliters of volume versus 0.5 milliliters of volume. So those are extensive properties. It depends on how much you have. But a lot of properties are intensive, and it doesn't depend on the amount of matter that's present. So, for example, the temperature of your substance, in theory, you can have a small amount or a large amount, but you could still measure it and that'd be okay. Density is another one. We'll talk about that later. Melting and boiling points. So both of these are important to think about. Like, does it matter how much you have, or does it not matter how much you have? And once in a while, that'll be important to us. So the properties of matter, very, very important. It's really nice to know if you have a metal, a non-metal, or a metalloid. Definitely important. Now, some of the elements sometimes have a non-metal, non-metalloid color, and you can see in the lower right-hand corner there's some white ones. Those white elements are usually brand new elements, so they honestly just don't know what's happening on them. They don't know if they're metals or non-metals or metalloids. Now, probably they're metals because they're kind of to the left of that metalloid line, which here is kind of pink, but they just don't know yet, so they're trying to be safe. A lot of times a periodic table will also tell you if you have a substance which is a solid, liquid, or gas. And if you look at the color of the symbol of the element, you can figure that out on this periodic table. So if you look at hydrogen up there, number 1, it has kind of a red H. That red in this one means it's a gas. Most of the elements on the periodic table have black letters. That's black means that it's a solid. So most substances at room temperature and pressure are solids. But if you look carefully, number 35, bromine, Br, and number 80, Hg, which is mercury, those are both blue. Those are two substances which are both liquid at room temperature and pressure. So it's kind of fun to see which ones there are. Again, most elements are black, so that means most elements are a solid. In the upper right-hand corner, as well as hydrogen, you have a few gases, definitely, and there's only 2 liquids. And again, that's at room temperature and pressure, and we'll talk about why that's important later. But that's the phase of the matter you're going to see normally, all right? And you can change phases, but the normal way, that's what you'd see. To measure something is a way to assess what you have, and measurements are definitely important. And if you're going to make a measurement, there's going to be a number and a unit associated with it. So the number is basically just to show the size or the magnitude of whatever you're looking at, and the unit is also important because it allows you to know what you're measuring. For example, in that value in the lower right-hand corner, you're measuring kilograms. You have 61.2 kilograms, which is mass, and that's a lot different than if you had 61.2 liters, which would be volume, or 61.2 seconds, which would be time. So both the number and the unit are very, very important. Now, one thing that drives chemists just something to think about, shall we say, when it comes to chemistry, is the uncertainty that's used. Because a lot of times you don't know for sure exactly how much you have. And we'll talk about that uncertainty and how that affects chemists in a little bit. Scientists will often use what's called an SI unit, which is basically a standard of units that scientists have agreed upon are kind of the ideal units, and they're really cool. The kilogram is the SI unit for mass, as well as the second for time and different things like that. Chemists often use SI units, but we always will sometimes use different kinds of units too. We'll see that as we go through the course. Here are the common types of units that are used. Length is usually in meters. That's the SI unit. Mass, as I said, is in kilograms, and time is in seconds. Temperature is usually recorded, officially anyway, in the Kelvin scale, which we'll talk about later. The other ones down there, amperes for current, which we'll use a little bit in Chem 223. Amount of substance is moles. We'll definitely talk about that. We don't talk about intensity of light very often, but if you do, it's the candela. So these are just things that scientists have agreed upon are pretty important. And it's not that you have to, for example, always use Kelvin temperatures for measuring temperature. We'll talk about how a lot of times when you're in the lab, chemists will use Celsius and convert to Kelvin. So Celsius is like the day-to-day version of temperature, but we'll convert to Kelvin when we're doing calculations, stuff like that. And there's lots of examples of this in chemistry and all the fields of science in general. It helps sometimes to figure out the magnitude, though, of what you've got. So, for example, if it comes to mass, the gram is kind of the base unit. But what if you have just like 1/10 of a gram, or maybe you have 1,000 grams, stuff like that. So the metric prefixes can be super helpful when it comes to mass. It also is really helpful when it comes to volume. It's helpful when it comes to time, all different kinds of things. And these metric prefixes are just terms that are used. So for example, if you had 1,000 grams, in scientific notation, 1,000 is 10 to the third. Well, 1,000 grams would be a kilogram. So you can see there the kilo, which has the symbol K, has a 10 to the third to it. And if you would then write right next to it a kilogram, that equals 10 to the third grams. So you can see there, like a kilogram is 10 to the third grams. But maybe you only have 1/1,000th of a gram. Well, 1/1,000th is 10 to the minus 3, which is above the kilo there. And you can see that 10 to the minus 3 is milli. So if you have a milligram, that equals 10 to the minus 3 grams. So metric prefixes can be really cool for representing large or small numbers depending on what you're using. And you can see there that there are 5 metric prefixes I really want you to know. I want you to memorize them because we're going to use them a lot. Nano, micro, milli, centa, kilo. Those 5 we're going to use quite a bit. And if we do use them, just you got to know what the prefix is. So milli, 10 to the minus 3, centa, 10 to the minus 2, etc. Now, micro there has a symbol M, and that is sometimes used. But another symbol that's used sometimes is what's called a mu. And it's a Greek letter. It looks like a U with a long kind of a tail in front of it. Mu is a lot of times used for micro as well. So just realize if you see that for micro, it's really important. I won't use little m for micro. I'll use little m for milli as I go through my stuff. But anyway, if you see them, just realize these are going to be important. And we'll see some examples of this here coming up. It's important to know the metric prefixes. Here's this poor person wishing for water, and this person sees a sign, water 9 kilometers or 50 meters. And they're like, oh, well, 9 is less than 50. I'll go for that. But, oh, man, a kilo is 1,000. So 9 kilometers would be 9 times 1,000, 9,000 meters. So it's farther to the water to the right than water to the left, which is only 50 meters. So it's very stupid and stuff, but you get the idea. Metrics might save your life one day. So we talked about mass, grams, kilograms, centigrams, all that kind of stuff. Another type of unit measurement that's really important in chemistry is length. And length is usually in terms of meters, which is the SI unit. So meters is important, but like before, you might have, say, 1,000 meters. And so knowing that 1,000 meters is a kilometer is important. On the other hand, if you had 1/1,000th of a meter, that would be a millimeter. So these kind of units can be really, really helpful. And again, it just depends on how much kind of area you have. Now, in terms of length, in the good old United States of America, we are still really entrenched in the old, what's called empirical units, or the American units. And those are yards and feet and inches, stuff like that. And so a yard is a little less than a meter, and an inch is a little bit bigger than a centimeter, stuff like that. We will only use metric conversions in this class, at least to the level that I can support it anyway. That'll be really important. It's nice to know how to translate though. So there's 2.54 centimeters per inch, stuff like that you can translate. But in this class, metrics are really cool. Everything based on powers of 10 are just so much easier than the other ways of doing things. It's crazy. So on the left-hand side there, I have some useful conversions. The metric prefix for centa, for example, is 10 to the minus 2. So in terms of length, which is what we're talking about, 1 centimeter would be 10 to the minus 2 meters. But what people do a lot of times is they put the number over on the centimeter side. So if you wanted to convert 10 to the minus 2 meters equals 1 centimeter and put the number on the other side, you would divide both sides by 10 to the minus 2. And in a nutshell, what that means is you end up with 100 centimeters, 10 to the positive 2 if you're into that. 100 centimeters equals 1 meter, and those are really important conversions to know. Same thing down there for the millimeters. 10 millimeters equals a centimeter, or 1,000 millimeters equals 1 meter. You can convert back and forth. We're going to use a lot of light measurements here pretty soon, and that's where the nanometer comes in. Now, the official metric prefix for nano is 10 to the minus 9, so there's 10 to the minus 9 meters per 1 nanometer, but sometimes then we'll talk about how there's 10 to the 9th nanometers per 1 meter, and they're both fine. You can use either one you want, but just realize that there's a little bit of a difference depending on which scale you're using. Length, by the way, is defined as the distance light travels in a vacuum in that much of a second, and we'll see where that number comes from in a little bit, but it's a pretty cool kind of definition. That's where length is actually defined as. Mass actually is measured in terms of a platinum iridium alloy, which is kept in France. And that's where the idea of the kilogram comes from, which is kind of crazy. So that's where all of the symbols are. There's many different replicas, and they always worry about corrosion of the sample, blah, 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 but it's really helpful. Mass is, again, in terms of grams. So kilograms, milligrams, and grams are used a lot. 1,000 milligrams equals 1 gram. 1,000 grams equals a kilogram. So those are the ones that we'll use frequently as we go through this course and just kind of realize it. In biology, though, you might use, for example, a microgram, which is 10 to the minus 6 grams equals 1 microgram. So just realize there's going to be a few differences depending on where you are and what you're doing. But you can do all of this if you understand how this stuff works. Time is also important. Time is going to be more important to us in the next chapters, but time, as you know, is measured in seconds, minutes, hours, days, years, decades, etc., etc. Most of the time, chemists are pretty cool using just seconds to minutes and minutes to hours. So there's 60 seconds in a minute, 60 minutes in an hour, stuff like that, which is kind of cool. Time is really an interesting topic, and it's beyond what we need to talk about right now, but different fields of science will kind of describe time in different ways. And you can read that little picture in the lower right-hand side right there. That's, again, more than we need to talk about in Chemistry 221, but it is a fascinating topic to talk about. And maybe if you're taking this class in person, I'll talk to you more about what I think about it too.